Hello everyone, welcome back. Today we have 2385 amount of time for binary tree to be infected. It says here that we're given the root of a binary tree with unique values and an integer start. At minute 0, an infection starts from the node with value start. Each minute, a node becomes infected if the node is currently uninfected, so it's not already infected, and the node is adjacent to an infected node, which means it's, spreading out. Return the number of minutes needed for the entire tree to be infected. Now, once again, each value is unique, and we are guaranteed that the tree will not be empty. It will have a start, it will have at least one node, and it will have a starting node, a node that is infected to start. And if that is the entirety of the tree, then we return 0, as in it takes 0 minutes to infect the entire tree. So this is really just a two-part problem. Part 1 is identifying all the relations, and that's part 1. And then part 2 is actually starting from the start node and visiting each relation and infecting them. Then, in the next iteration, those infected nodes become the new hotspots, and from there, for the range of those hotspots, we do the infecting, we spread out, we infect, and that's another minute of processing. At the end, we return the total number of minutes taken to infect the entire tree. So let's start with the first part, which is identifying all the relations. We can initialize a default of list. So it's a mapping where the key is the node's value, which we're guaranteed to be unique. So some value or node.value, and the value is by default an empty list. Otherwise, it's neighbors. Neighbor 1, neighbor 2, and so on. Okay, and then we'll have some stack where we'll start it with our root node, which we're given, and the incoming parent. So for the root, that's actually empty. There is no incoming parent. And then we'll say while stack is not empty, we're going to have some node and some parent from which the node came. So let's pop that off the stack and say if there is a parent. Now, if there's no parent, there's no relation to jog down. There's no connection that we need to track, so that's all right. But if there is a parent, then we want to add it to each adjacency list. So graph of parent.val, we want to append to this empty list or to this list the node.val, right? And then to the other guy, the node.val, we want to append the parent.val. So we're just tracking the two-way relation. Then also, now let's say we're here, we want to say if there is a left node, we want to process that too. So if there is a node.left, then into stack, we want to append for future processing the node.left as the next node, and as the incoming parent node this time, it'll be our current node. Our current node is the parent node, and then the next node will be the node here. Okay, and then likewise, if node has a right child, then we want to add to processing with the correct number of P's. We want to add to processing node.right with, once again, our outbound node as the parent node. Then for sake of spacing, let's do that. All right. Then at the end of this, we should have a dictionary where the key is each of these values, and the value will be a list of all its relations. So for instance, 6 would have a connection to 3, 3 will have a connection to 6, 10, and 1, such and such. Okay? So that's part 1. We have the relations. Now part 2. Part 2, Okay, part 2, we're tracking the seconds and we're going to initialize it as -1 because in the event that the start node is all there is, we know we're going to increment or keep track of the number of minutes that pass. If by the end of that first iteration we're done, then this will increment to 0, and 0 is what we want to return. So we'll initialize res as -1 and say we're going to keep track of all the nodes that we've seen. And this will start with start. So these are the nodes which are already infected. Okay, and then we have a queue, which is QE, and this will also start with our start node, and this will be our spreaders. So these are the nodes that are already infected that have not itself yet infected its own neighbors. And then while such nodes exist, we can say for each of those hotspots, so whatever the current current queue size is, that's for that iteration, we'll say the spreader is whatever QUE dot left pop. We'll take the first node. That's our spreader, and now the ones who are susceptible to the infection are the neighbors. So let's grab the neighbors. So we'll say for neighbor in the graph of this current spreader, we'll say if the node is not infected, so if neighbor, which is next to the spreader, if neighbor is not in scene, as in not already infected, then we can infect it. So this neighbor is now infected. And now this neighbor, QEUE, is also going to be the new super spreader or spreader. So append NEIGHPUR. And this will be a new spreader. Okay, and these will create the new zones. And at the end of this batch, so we're processing the entire batch for every minute. So at 1 minute, we're processing the current state of hotspots. And once we're done processing this, we may, and at least in the start, we'll definitely have more, we'll then process that next state of hotspots. Okay, and then at the end of that processing, make sure to increment res, and at the end, we just return res. And it looks like, okay, let's give that a go. Oh, deck left to pop. Do I have Q dot? Oh, I think it's pop left. Pop left. Left pop. Pop left. Okay, let's give that a go. And there we have it. Let me expand this. So once again, this is 2385, amount of time for binary tree to be infected. The idea is actually quite simple, which is you just need to know all the relations, and you start at the root because these are outbound. You can tell what all the children are by starting at the root, so that's where you start the stack collection. Then once you have the graph of relations, you can go about infecting. You can go about doing the spreading process, and for each round of spreading you can increment res. And remember, we initialize res at -1 because should the case be that this tree has only one node and the one node is infected, we're going to be done after this node is processed. So once this one iteration is done, we'll increment this to 0 and we'll be returning 0. Thanks so much. Happy coding. See you next time.